If you have to know the answer right away, it's no. Or at least my goal with this video is to convince you that the world is not running out of sand. But if it were that simple, I wouldn't be here, right? And you probably wouldn't be either. In fact, I was really surprised by some of the things I didn't know as I dug deeper into the topic, and how some of the most widely spread sand facts are dead wrong. The wide world of sand is complicated, and not in a boring, pedantic kind of way. This simple
Before he continues, basically he was answering the question of the initial video of, is the world really running out of sand? Candidly, I didn't realize this was something people thought was happening. So it's definitely piqued my interest to understand what is leading to folks having this perception, and what is actually kind of at the root of that problem.
material touches nearly every part of our lives, and the science and engineering behind it is rich and deep, and to me at least, hard not to become obsessed with. There's a good chance you've seen articles or videos over the past few years with essentially the same story about sand. The Sand Wars documentary kind of kicked off the modern discussion, and then Vince Beiser wrote an excellent book on the topic, The World in a Grain. Of course, a lot of the book's best reviews focus on the fact that sand is kind of a topic that's taken for granted or neglected, but at least in civil engineering, it's one of the most neglected materials out there, and I'd like to give you a peek behind the curtain and show you how we think about this seemingly unlimited resource and why it's worth knowing a little bit more about it. But first, I need to head out to the garage and put some sand in a rock tumbler, because I want to do a material properties shootout, and this is going to take a little while. I have something pretty cool in the other barrel, and I'll show it to you later on in the video. I'm Grady, and this is Practical Engineering. What the heck is sand anyway? It's kind of a know it when you see it type material. If we use the US Department of Agriculture soil textural triangle, sand is any granular material that is at least 85% sand. So what the heck is sand? For a better answer, we have the Unified Soil Classification System. Geotechnical engineers sometimes say that dirt is a four-letter word, maybe because it undermines the importance of soil, which is also a four-letter word by the way, but I like to think it's because we have better names for all the dirts around the world, and here they are. In fact, there are 4 specific kinds of sand, but they all fit this one criterion, and it's all about the size of the particles. At least half of those particles have to make it through a number 4 sieve, about 5 millimeters, but no more than half can go through a number 200 sieve, less than 1/10 of a millimeter or 75 microns. That is a pretty wide range of materials, but I think when you picture sand in your mind, you probably imagine what the USCS would call clean sand, where less than 12% pass the 200 sieve. So just to make it simple, let's say that sand is a material where the particles fit through this, but they don't fit through this. But still, that encompasses a huge range of different dirts, and I hope at this point you're asking, who cares? Because I would love to answer that question. In his book, Beiser calls sand the most important solid substance on Earth, the literal foundation of modern civilization. We use it to make glass, semiconductors, fiber optics, filters, and abrasives, use it to texture surfaces, to play in, for beauty, and more. But probably more than anything else, sand is an essential ingredient in concrete. And you know, I'm a civil engineer. This is a channel about the built environment, so I want to talk about concrete. And in fact, if this video sparks your curiosity about one of my favorite materials, I have a whole playlist of topics I've covered in the past so you can learn more after this. You can't really overstate how important concrete is and how much of it we use. There's a bigger conversation to be had about its environmental impacts, but when compared to alternative building materials, it just has so much going for it. It is an extremely low-cost, durable substance that can be made into just about any shape you can imagine. Concrete has enabled us to build structures that last for generations from some very simple ingredients that are mostly available across the world: water, cement, gravel, and sand. Most of those ingredients are mined and used directly as raw materials, and they're usually mined close by. Transportation makes up a big part of the cost associated with sands used for construction, so the distance between where they're found and where they need to go is highly correlated with how economical they can be. and that often leads to environmental impacts, some worse than others, depending on local regulations. It turns out that the best sand for concrete often comes from rivers, and mining in rivers can be particularly destructive because the impacts can spread upstream and downstream through changes in the nature of the channel. I have a series of videos on that topic too, by the way. Sand isn't spread evenly throughout the world, and it's a non-renewable resource. Geologic processes produce it a lot slower than we can use it. So it makes some intuitive sense to say we could eventually run out. But here's a fact that's often overlooked in the discussion. We can make sand. And it's not that complicated either. I talked about the definition of sand a little earlier, but here's another one. It's just very small rocks, and we've engineered machines that can transform big rocks into small ones. In fact, I have such a machine in my garage. It's called a hammer. Some might argue.
Yeah, so this is an interesting aspect, which is, I guess, fundamentally why I didn't realize folks were discussing sand was running out. I guess it makes sense that like naturally occurring sand potentially is obviously a finite resource, but my expectation had always been you could just make more sand. Like they had highlighted rivers there, and I think most of that occurs due to like erosion and then like slowly kind of breaking down rocks and other minerals to create that sand. So that natural process almost certainly could be replicated with human intervention. So curious as to how this became a question to begin with. Maybe I'll have to check out that video and that book.
This isn't the best use of my time, but I spend about an hour to artisanally manufacture a batch of sand just to hammer this point home. First, you crush the rocks. Then you put them through sieves to remove the stuff that's too big or too small. It takes a little extra processing, but this isn't grain surgery. And this has a lot of benefits compared to sourcing natural sand. Hard rock quarries and crushing operations are already out there producing coarse aggregates like gravel. So sometimes the smaller stuff is a waste product anyway. It opens up possibilities when natural deposits aren't available and can move mining operations upland away from rivers where the environmental impacts are less severe. And it can make the concrete stronger. Let me show you what I mean. I took some sand out of my kid's sandbox and put it in a rock tumbler for a week to try and simulate the erosion it might see over years in windswept dunes of a desert. Obviously, this erosion reduced the overall size of the particles, so I classified both materials with sieves to make them a closer match for a fairer comparison. And both batches are within the spec for concrete sand in the US. Looking in the microscope, you can clearly see the differences. The tumbled sand is rounded with roughly spherical, smooth grains. The manufactured sand is jagged with sharp, angular corners. And watch what happens when I pile them up. I filled up 2 pieces of pipe with the same amount of sand and then pulled the pipe away. It's not a huge difference, but you can see the rounded sand spreads out a little further because the particles have less friction. It makes intuitive sense that concrete made from this sand would be weaker than with this sand. Let's see if that's true. I mixed up a simple batch of concrete from the crushed sand and the tumbled sand, keeping the weights of all the ingredients equal. Here's my recipe if you want to try this experiment yourself. Then I molded some concrete cylinders and let them cure for a week. Most concrete mixes are meant to reach their design strength after 28 days, but concrete strength gain is fairly predictable, so the relative difference between the samples should be consistent in time. Most importantly, my little benchtop hydraulic press would not be able to break these samples if I waited that long. And this load cell is not calibrated, so I'm doing this test in arbitrary, practical engineering units of force. The tumbled sand cylinder broke at around 2,500 units, and the manufactured sand concrete broke at 7,500 units. You can easily see the difference in the results.
Good night.
It was 3 times as strong. Of course,
That's actually an awesome little experiment that he had at his home. I guess I'm not sure if every civil engineer has one of these machines at their home or if it's just this individual for the sake of this experiment or other similar ones. But that is an interesting idea. So he's basically highlighting the fact that the different forms of creation of sand, the tumbled one basically creates a rounded form of sand, which then impacts its durability and its structure, which makes sense versus sort of like the shattered version that he made from the impacts. So curious if tumbling is the standard form. I'm not entirely sure why he showed that as one of the examples currently. Maybe that's one of the main manufacturing methods, but we'll see if he explains that more.
This is my garage, not a testing lab, and I only did one sample because my arm got tired of hammering rocks. Luckily, people much smarter than me have tested this out, and the results are pretty conclusive that if you keep everything the same, the angularity of fine aggregate increases the strength of concrete. And that's probably the story you know if you've read anything on this topic. It's the common explanation for why we don't use dune sand, the most visible of Earth's sand resources, in concrete. It's intuitive.
That makes sense. So he was highlighting dune sand. That was the point of the tumbling, which was to kind of highlight that is what would mimic that type of structure, and just highlighting the fact that dune sand is basically structurally less resilient. While, again, being a software engineer myself, I'm certainly nowhere near the level of expertise as this individual. But if I remember anything from some type of engineering classes like this, I'm pretty sure they always highlighted like triangles being a very solid form of structure. I think they help distribute weight, etc. So that this could be, again, since he's primarily highlighting basically like the geometry of the sand, that how that is structured would theoretically, there would have to be a premise for why it does benefit the structural integrity of the cement. So curious if he'll get into that more here.
If rounded grains don't lock together. Beiser makes the claim not once but 3 times in his book. But it turns out it's not that simple, because strength isn't the only property of concrete that we care about. Before concrete has to be strong, it has to be placed. Ask anyone who's done this kind of work and they'll tell you it's hard. Well, it's liquid at first, but it's hard to work with. Concrete is about 2.5 times the density of water. It's heavy stuff, and to get it into the forms often can require a lot of different tools. Wheelbarrows, buggies, chutes, pumps, hoses, and more. The better the concrete flows, the easier it is to do a good job placing it. And that matters. If a mix is too stiff, it can clog up hoses, trap air bubbles, and ultimately lead to poor quality in the installed product. This property of concrete is usually called workability. It's often measured using a slump test. Fill up a cone of concrete, pull the cone away, and see how far the concrete slumps. But the problem with workability is that in one big way, it works against strength, and it all has to do with water. What happens when the concrete truck shows up to your job site and the mix is too stiff? Depends on if the engineer is there or not, but in a lot of cases, you just tell the driver to add a few gallons of water to the mix. More water, better flow, easier to place. It's pretty straightforward, but there's a reason you don't want the engineer to know. Water decreases concrete strength. I've done a whole video about this with some garage demos, so again, check that out if you want to learn more. The gist is that the ratio of water to cement is one of the most important factors determining concrete strength when it cures. Cement isn't like some types of glue that harden as the water or solvent evaporates. It goes through a chemical reaction, incorporating the water into the final product. That's why we say concrete cures instead of dries. But cement can only react with around 35% of its weight in water. So any more than that is just taking up volume in the mix that could be used by the stronger ingredients. More water, less strong. And here's where the shape of the grains comes into play. I did a little garage slump test to gauge the workability of these 2 mixes I made for the earlier demonstration. Here's the rounded sand mix, and here's the manufactured sand. No slump.
That's definitely noticeably different. Also, I guess if you were thinking about it in another way, like if you had a stack of marbles, they would certainly, you'd expect them, if they were in a cylinder, to kind of move outwards, versus like if you had dice, for instance, in a cylinder, if they were stacked up like this, they would stay there more naturally. So in this sense, it does seem to be because it's rounded. He did highlight something about it being cured, concrete being cured instead of dried. I'm curious if this is some factor of which cement is effectively considered just like a very, very viscous liquid over time, not necessarily actually transitioning from a liquid to a solid. And maybe that rounded segment allows it to kind of like move outwards, like it is doing here when it's in a more liquid form.
At all. Honestly, I expected this to be a subtle difference, but it was like night and day. They weren't even close. So I wondered what would happen if instead of holding ingredient ratios constant, I used the workability as the controlled variable. Let's find out. First, I used the manufactured sand with enough water to get it to a workable level. 100 milliliters got it to here, which is a bit better than the first one. Then I did a second mix with the tumbled sand, slowly adding water and running the slump test until it was pretty close. It took only 70 milliliters of water to make them match, 30% less than the first batch. After a week, I tested the samples. The tumbled sand broke at 4,800 units, and the manufactured sand broke at only 4,300 units. The tumbled sand with the rounder grains was stronger this time, by about 10%, and it's all due to the lower water content in the mix.
Interesting. So this could be another factor that he's covering, which is potentially due to the rounder element and how workable it becomes, that actually using standard practices is maybe introducing too much liquid or too much water into the mix, which is like overdoing kind of its workability in this case. This is actually a very interesting video and experiment that he has set up here.
So yes, if you use the same amount of water, more angular sand like you might find from a river or manufactured sand is better, but that's not what happens in real construction. I say this with many caveats, but very generally, you only add as much water as you need for workability. Rounded sand gives you better workability so you can add less water and thus get stronger concrete.
So he had basically previously highlighted the fact that folks don't usually use dune sand for its geometry. Here he's highlighting that it's actually totally possible as long as you control for how much water you put in. So I wonder if he's going to circle back to that point in a bit.
This idea that we can't use wind-blown sands in concrete because of their shape is a myth. In fact, the American Concrete Institute has a bulletin that says it better than I can. The influence of fine aggregate shape and texture on the strength of hardened concrete is almost entirely related to the resulting water-to-cement ratio of the concrete. I tried to track down the original source of this idea that we can't use rounded grains in concrete, but got nowhere. Beiser cites an article from the UN, which itself cites a 2006 paper about using two types of desert sand from China in concrete. But that paper doesn't mention the roundness of the particles at all. They didn't include any measure of the shape of the grains in their study, and they didn't make any suggestions about how that particular property of desert sand may have affected the results of their tests. In fact, the conclusion of the paper includes saying that desert sand is a feasible alternative to other types of fine aggregates used in concrete. And the whole reason it was the subject of scientific study at all had to do with size, not shape. This is a widely used specification for the distribution of particle sizes of fine aggregate for concrete. Any sand in this area meets the spec. And here's the soil used in that paper. Even if the conclusion was that it didn't work, I think this would have a lot more to do with the results than the shape of the particles. And that really gets to the heart of this whole discussion. Fine aggregates are found throughout the world. We can even make our own. And concrete is like baking. Different ingredients can change the end results, but just like regional bread recipes evolved based on the availability of local ingredients, the construction industry has developed a lot of ways to use different local materials to achieve good structural properties. The real challenge, like many things in engineering, is cost. It can be more expensive to manufacture sand compared to mining raw materials that can be put directly in a mix, especially when you factor in other ingredients like chemical admixtures that might be required to make it more workable without adding too much water. It's expensive to transport better quality sand from far away, rather than finding it close to a job site or batch plant. It's expensive to mine sand in adherence to environmental regulations that are becoming stricter worldwide. It's catchy to say there's a scarcity of fine aggregates on Earth, but I think it's misleading. Sand is getting a lot more expensive than it used to be, just doesn't make as nice a headline. And the tricky part is that in many ways, those costs have always been there. We've just externalized them onto the environment and our future. All the ingredients in concrete are mined or harvested just like other natural resources. It's just that concrete is made on a scale that blows most other materials out of the water. It's a huge business, and there's lots of money flowing, which means a lot of potential environmental harm and social conflict as a result. That's especially true in places that don't have a robust oversight and enforcement of how sand is extracted. And I think it's important to point out that the low cost of sand, because of its simplicity as a material and its abundance, is a big part of why we use so much concrete in the first place, even in situations where it's not necessarily the best material choice in other respects. Everything in engineering is a trade-off, and if the economics around sand change, the engineering and construction industries can change with them. Look at other examples of this. Diamond used to be exclusively a mined material, but now we can make it in a lab. Synthetic diamond gemstones used in jewelry are now less expensive than mined diamonds, but admittedly, there's a lot more to that economy than the cost to make them. What I think is more interesting is that 99% of diamond used in the world for industrial purposes is synthetic. It used to be a rare mineral, and now you can pick up a diamond drill bit or saw blade from the hardware store for a fairly small premium. Timber is another example. Natural forests used to be the only source, but now plantations, trees planted specifically for harvest, now make up more than a third of the wood we use globally. And engineered lumber like plywood, OSB, and structural composites can make more efficient use of raw materials. I'm pointing out these examples not to say they're good or bad, there are pros and cons in both cases, but just to illustrate how our demand for materials in the construction industry changes with the supply, and how technology can have a huge impact on that. And there's another parallel between timber and sand. They both can be renewable. I had another barrel in the rock tumbler not going to use, so I broke up some chunks of concrete and threw them in. I ran these through the grits just like you would with any other rock in a tumbler. Concrete is pretty soft compared to most natural rocks, so it didn't polish up that nicely, but the result is still pretty cool. You can see the constituent materials of the concrete after it spent so long rolling around in there. The small and large aggregates and the cement paste locking them together. But the point of this demo is that concrete is pretty much just rock. That's mostly what it's made of in the first place, and just like the rocks I crushed to create the manufactured sand, concrete can be recycled into aggregates that get reused in the construction industry, either in new concrete or other materials, reducing demand for virgin sources.
Yeah, that's a great point that he's making there. Which was my expectation as well, which is it's not like the sand got destroyed or the aggregate got destroyed in the making of cement. So it does seem to be the premise of running out of sand is more of an exaggeration to basically highlight the fact that sand is getting more expensive, again, because like other natural resources like oil, etc., there was a natural repository of it within nature over time as it accumulated. And as humans have started to take advantage of those areas and the amount that was there, we can start to overuse those substances to the point where they are no longer sustainable. So this seems to be mostly highlighting the fact that sand is something that we are using a lot of, probably more quickly than nature is generating it at this point in time. And so now alternatives are becoming necessary in order to help make it sustainable in the future. But this is a great video overall.
There's a lot changing in the construction industry and a lot of growth in the need for materials like sand and gravel, but I don't think it's fair to say the world is running out of those materials. We're just more aware of all the costs involved in procuring them, and hopefully taking more account for how they affect our future and the environment. I love diving into the nitty-gritty details of stuff we normally don't think about. Of course, as an engineer, I focus on the built environment, but there are topics like sand in just about every field, a lot of them covered by my friend Sam from Windover Productions in his series The Logistics of X. From coal mining to search and rescue to ski resorts, these videos just scratch a particular itch to learn about underappreciated parts of the world. This one on the logistics of Hajj covers all the complicated details of hosting 2 million visitors from all over the world in Mecca every year. And if you want to check it out, it's available to watch on Nebula. I talk about Nebula a lot. It's a streaming service built by and for independent creators, and it's growing super fast. After the major overhaul of the homepage, making it easier to find new stuff to love, we've leaned into producing really good, original content like The Logistics of X. Basically allowing your favorite creators to make bigger budget videos with more resources and without the pressure from advertisers or sponsors. That means you get more creative, interesting, and thoughtful videos. My videos go live on Nebula before they come out here, and right now a subscription is 40% off at the link in the description. Plus, if you already have a subscription, now you can gift one to a friend. Give yourself or someone you love a year's worth of thoughtful videos, podcasts, and classes from their favorite creators. It's 40% off either way at nebula.tv/practical engineering. Thank you for watching, and let me know what you think.
Like what he said, thank you for watching. Hopefully you enjoyed what you saw. If so, please hit like or subscribe. I will see you around.